So we're talking about rotational dynamics, which is the equivalent of translational dynamics. So torque is our equivalent of force. But in order to talk about rotational dynamics, we have to actually figure out what the proportion is. And rotational inertia is going to be our connecting point. So we left off with the proportionality of rotational acceleration and net torque. This is still Newton's second law, just like for translational motion, acceleration is proportional to net force. So what is the exact relationship for translational motion? Is acceleration is going to be equal to the net force divided by the mass. That is Newton's second law rearranged for acceleration, and that is how we originally wrote it. So what we're going to want to know is to actually solve and set up what's going to take the place of mass for rotational dynamics. Because for translational, all you need is mass. For rotational, it's a little bit more complex. Just like we need force and the lever arm, we're going to need mass and for determining the exact relationship. And in order to do that, we're going to start with the simplest possible situation. A particle that has mass rotating around an axis at radius r. We're going to assume that everything except for this particle of mass m has a negligible mass. This mass m is rotating at radius r, and it's experiencing this force right here. So there is a force acting on that mass, and that force is given by this value F. So we could calculate the torque as this perpendicular lever arm to that force, and that force equals mass times acceleration. So that means that if we want to know the relationship for rotational acceleration, what we're going to do is we're going to say that A equals R alpha, and we're going to swap that in right there. So that means that the force equals mass times R times alpha. So if I want to turn that into torque, then I have to multiply both sides by R. And so if I multiply both sides by R, times R there, times R there, FR equals torque. And then mass, radius squared, and rotational acceleration. So here it is. Here is our version of Newton's second law for rotational motion, where for translational motion it was F equals ma. Now for rotational motion, it's torque equals mr squared alpha. Here, the role of mass is being played by this mr squared value. This mr squared value, for the simplest possible situation, is rotational inertia. And that's just the inertia of the movement of this particle right here. So let's say you have more than one particle, right? Or you have more than one force. Well, then you would look at the net torque. And the net torque would be made up of the net value, mr squared, for all of the particles, times the rotational acceleration. And we know for a rigid object, the rotational acceleration is the same everywhere. So what is the sum of mr squared for all of the particles involved in a system? Well, the sum mr squared for all of the particles in the system would just be, well, you take the mass of the first particle times the radius squared of that particle and add it to the mass of the second particle times the radius squared of that particle, and then add that to the mass of the third particle times the radius squared, and you do that forever. And the sum of all of those values would be given by this equation here. And we would give that value right there the name moment of inertia, and we give it the symbol I. So breaking it down, we say the moment of inertia, aka the rotational inertia, is given as the symbol I, and I is just the sum of the rotational inertia of all of the particles in a system. So if there's 3 particles in the system, it would be mr squared 1, mr squared 2, mr squared 3. Add them together, you've got your moment of inertia. We can remember mr squared, the sum of mr squared equals torque, and that's the net torque. Well, here I can replace this value here with an I, and then I get that the net torque is equal to moment of inertia times rotational acceleration. And there it is. That's rotational Newton's second law. Should look just like this, where rotational inertia is playing the role of mass. So what does rotational inertia do? What is its role? It's just like mass for translational motion, which means that it's going to do the same thing as mass would. So a larger mass would make something harder to get moving if we're talking about translational motion. Or a larger mass would have more momentum if it were moving. A larger rotational inertia would have the exact same features. It plays the same role as mass. So if we had these two cylinders and we said that this cylinder's mass and this cylinder's mass are the same thing, for translational motion, all of their motion would be given as equivalent, right? They would have the same velocity for the same momentum. But for rotational inertia, the shape is going to play a role, because here there's a particle way out here against this radius r, so that radius squared times that particle is going to give a larger value than this particle out here to that really small radius squared times that particle's mass. And so that means that overall this value right here is going to have a larger rotational inertia, and this particle over this object over here of the same mass is going to have a smaller rotational inertia. So just like something with more mass, something with a larger rotational inertia is going to be harder to start it rolling, and it's going to be harder to stop it rolling once it's going. And this over here, it's going to be much easier to start and stop its rolling. Rotational inertia is not just about the mass of the object. We're also looking at how that mass is distributed throughout. So that means that while for translational motion it was all well and good for us to accept that the mass of an object was just considered to be acting at and working at the center of mass, we can't do that for rotational motion anymore. We have to look at how that mass is distributed all around. So that means that we're going to have to every single time find the sum of mr squared. And if you're anything like me, you're probably thinking that that's a moment that's created by nightmares. So let's go ahead and let's look at a calculation for a really simple system first. All right, we're going to look at weights of different values on a bar with different axes of rotation. In the first situation, situation A, we're going to consider the axis of rotation, or the point at which the bar is going to move up or down, right at the center point. And it's a 4-meter long bar. And we're going to consider that the bar itself is massless, or has negligible mass compared to the two masses that are set on it. We know that that's not a real-world situation. It's about as close as we can get. So if this is a mass and this is a mass, and we wanted to know the moment of inertia of this system right here, I would equal the sum of mr squared. And here we've got two masses that we want to consider, so it's going to be m1r1 squared plus m2r2 squared, and we're just going to add them together. So 5 kilograms times, this axis is at the midpoint, so the midpoint of 4 meters is 2 meters, and that value is squared, plus the next mass is 7 kilograms, and its midpoint is 2.0 kilograms, 2.0 meters, sorry, squared. So here we have 5 times 4 is 20 kilogram meters squared, plus 7 times 4 is 28 kilogram meters squared. So the inertia for situation A, moment of inertia, is 20 and 28, or 48 kilogram meters squared. Hope I did my math right there. In situation B, we change it. It's still a 4-meter long bar, but now we're setting the axis of rotation, or the point at which it will rotate, all the way over here at this end. So that means that the radius from the axis of rotation is going to be different for bar 1 and for mass 1 and mass 2. The moment of inertia for object at point B is still going to be the sum of the masses times their radius squared. M1 is still 5.0 kilograms, but here the radius is 0.5 meters, and so that value is going to get squared. And the second mass, M2, is still 7 kilograms. But here now it's separated by 4.5 meters, and that value is going to be squared because it is separated by 4.5 meters from its axis of rotation. So here now we have 5 times 0.5 squared is 1.3 kilogram meters squared, plus 7 times 4.5 squared is 142 kilogram meters per second square, or meters squared. So that's going to give us a total of about 143 kilogram meters squared. So same masses, same length bar. When the axis of rotation was around the midpoint, the moment of inertia was 48 kilogram meters squared. When the axis of rotation was on the end and we had a heavy mass far away from the axis of rotation, we've more than tripled our moment of inertia. And so that means that that bar is not only going to be harder to start swinging, it's also going to be harder to stop swinging. And so when you consider the potential momentum of that bar, oof, way to go, good luck. So in this bar, we considered the bar itself to be massless, or have a mass that we could ignore. And that's not a real situation, because everybody knows that when you're adding weights to a bar, you start with the initial mass of the bar, and then you add these masses onto it, which means that we would have to consider every single particle in the bar and these masses over here according to their radius based on where their axis of rotation is. And that seems like it's getting to be a super complex calculation, which doesn't sound very fun. Ordinary objects are complicated. Their mass is distributed all throughout their entire system. So that means that actually calculating the sum of every single point that has a mass in that object is hard to calculate without calculus. Luckily, someone else has done the calculus for you, and they've come up with equations for regular simple objects. So if you take a look here, any object that's a simple continuous shape, right, that has a description, a thin hoop with a radius, right, you're assuming that any depth is negligible. Here, this is a thin loop that has a radius or a width. Here's a solid cylinder, like a can of soup. Here's a hollow cylinder, like an empty can of soup. Here's a perfect uniform sphere, like a steel marble. Here's a long uniform rod, like a barbell that you're lifting. Here's another long uniform rod. This long uniform rod is for an axis of rotation through the center. This long uniform rod is for a situation where the axis of rotation is at the end of the bar. And then last, a rectangular thin plane, right? Like this would be like a 2x4 board. Right, and so here is the actual equation that you can use to calculate the moment of inertia if you need to. I know that that doesn't sound super fun, but trust me, it's a lot more fun than not being able to do this without calculus. So make sure to keep this sheet right here, which is also found in your textbook, handy when you're problem solving.